Today we will discuss about chemical shift. What do you mean by chemical shift? Experimentally, it has been observed that a nucleus may have a different resonant frequency for a given applied field in different chemical compounds. That means what? See, when you consider, just as an example I am writing here, say this one is A, X is a compound. So another one is XA is another compound. Now I am considering the nucleus A. So the resonant frequency in this compound of nucleus A is omega 1. That means when the applied frequency equal to omega 1, the NMR takes place, that is nuclear magnetic resonance takes place. But in this compound, for the same nucleus A, the resonant frequency is omega 2. Even though the nucleus is the same, say proton here also it is the same proton. But the resonant frequencies are different. The difference in resonant frequency is called chemical shift. That is omega 1 difference omega 2 is equal to delta omega. This is called chemical shift. So, the shift is believed to be arised because the difference in the shielding of the nuclear moment when the chemical environment is changed, since the electronic configuration of a molecule depends on the chemical binding. So that means here you can observe the shielding. This A is having the chemical binding with X and X. Here it is only with X. So that means the shielding here is different compared to here. As the shielding changes, the resonant frequency is also changes. See, because the shift is observed only for chemical compounds and not for ions or free atoms. So it appears that it is second order paramagnetic term. See, when you consider an example of the fine structure of ethyl alcohol, that is C2CH5OH. So, this is, let us reconsider ethyl alcohol CH3CH2OH. Right. Now, when you observe the fine structure of ethyl alcohol, we are observing three different peaks. That means when you are considering to this, the three lines correspond to protons in CH3, in CH2 and OH group. So that means when you consider here, see, this is C, H, 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 then this is C, H, H, this is OH. So now you calculate the resonant frequency present in the of proton present in carbon nucleus, here also in carbon nucleus, here in oxygen. So remember, we are calculating the resonant frequency for protons. So therefore, when you determine experimentally and if you observe the fine structure, when in the absorption graph we are getting, see, absorption versus frequency, we are getting three peaks. So that means what? One peak correspond to the protons present in CH3. Second peak correspond to the proton present in CH2, and third one, the protons present in OH group. So as the shielding is different in these three groups, the protons get resonated at different frequencies. So in CH3 it resonated at omega 1. In CH2 group, protons get resonated at omega 2, and in OH group at omega 3. Omega 1 difference omega 2 or omega 2 difference omega 3, that is nothing but chemical shift. So in order for the chemical analysis, we can make use of this concept chemical shift. Next is quadrupole effect. Quadrupole effect. What is this quadrupole effect? Let us see. See, quadrupole moment Q, we know. The concept of quadrupole moment is used to explain the shape of the nucleus, whether the nucleus is spherical in shape or whether it is in ellipsoidal in nature. So whether it is oblate ellipsoid or prolate ellipsoid. If quadrupole moment Q is equal to 0, then nucleus is spherical in shape. So, but if Q greater than 0 or Q less than 0, then it is ellipsoidal in nature. So, therefore, here that means what? A nuclear electric quadrupole moment arises from a non-spherical arrangement of charge on the nucleus. So, now let us consider a nuclei with nuclear spin I greater than half. I represent nuclear spin. So now what happens? This nucleus is subjected to external DC magnetic field. That means now when you are considering to this, see, this is the single energy level. Now that means this is for I. But this is subjected to external magnetic field. Then the nuclear angular momentum vector can take 2I plus 1 orientations in an external field. That means single energy level split into 2I plus 1 sublevels. So that means what? Consequently, we will get single energy level when magnetic field is 0, but when the magnetic field is greater than 0, what happens? Each level split into 2I plus 1 energy levels. Single energy level split into 2I plus 1 energy levels. Then what happens? The transitions takes place between these energy levels. That means, as an example, let us consider I is equal to 3 by 2. So, in the absence of field for I is equal to 3 by 2, you have single energy level. If you apply the magnetic field, it split into 2I plus 1 levels. That means 2 into 3 by 2 plus 1 is equal to 4. That means this single energy level split into 4 levels. So that means this is the case. So all energy levels. Then When electromagnetic radiations are made to incident on the sample, this is when H is equal to 0, this is H greater than 0 for I is equal to 3 by 2. Then what happens? The transitions takes place between these energy levels leading to H nu naught. Here also H nu naught because all are equally placed H nu naught. That means here all three peaks superimpose and we will get single peak because all peaks are having the same intensity or having the same frequencies emitted during the transition. Now, but this is the case when we are observing for Q is equal to 0. But in some crystal, an additional splitting is caused. So that means we are getting not only single peak, we are getting 3 peaks say for these energy levels. Okay. So that means what? How you are getting this? What is the reason for this? The reason for this is a quadrupole moment, that is non-spherical shape of the nucleus. When the nucleus is not spherical, what happens? Nucleus produces the quadrupole moment. So therefore the energy of electric quadrupole moment, energy of electric quadrupole moment is given by Q into E. It is the product of quadrupole moment and charge, that is equal to half integration rho 3 z square minus r into dV. So where r rho is the charge density, then dV is the volume element, r is the distance from the center of the nucleus, z is the coordinate along the symmetry axis of the nucleus. So that means now the effect of quadrupole moment is it like a electric field is now acting on it. That means additional splitting is caused due to the interaction of nuclei with the electric field. Because of this, what happens? The additional splitting takes place. Like this. So here, when the transition takes between these two, the energy H nu naught is released. In this transition, H into nu naught plus delta nu. Here H into nu naught minus delta nu. But the selection rule, delta mi should be plus or minus 1. That is, if it is plus half 3 by 2, so minus half minus 3 by 2. So therefore this is the value of I in the presence of electric field. So because of this, what happens? In non-spherical crystals, instead of single peak, we are observing 3 peaks. So this effect is called quadrupole effect. Next, let us see the instrumentation of NMR. Instrumentation. Just it consists. See, this is the sample tube. Now here you have RF transmitter, radio frequency transmitter. So that means in order to, this is to produce the radio frequency. So that is radio frequency means radio frequency, it is the electromagnetic radiation to produce this. So then here you have RF receiver, radio frequency receiver. So here the coil is wounded. RF receiver. Then here you have RF amplifier. So then for producing the static magnetic field, you have a powerful homogeneous electromagnets. Magnet. Then here you have sweep coils. So this is the sweep generator. It is the sweep generator. Then this is nothing but oscilloscope to observe the resonant curves. RF amplifier is also connected here. See, in this is the transmission coil. Transmission coil. This is to receiver coil, right? So now the sample is placed in the sample tube. Then in the usual experiment, what we are doing is switch on the electromagnet first, then apply a particular radio frequency. Then what happens is, you slowly, here you have, it is sweep coils you have. This is nothing but sweep coil. So that means this sweep coil is connected to the sweep generator. Slowly you have to vary the current in the sweep generator. Now what happens is, the strength of the static magnetic field. Now this also produces static magnetic field. So these are the two powerful magnets it produces. Now apply, switch on these electromagnets, switch on RF transmitter, it sends radio frequency of a particular frequency. Okay. Then what happens? You have to slowly vary the current in the sweep coil so that it produces DC or static magnetic field. So as you vary the current in the sweep generator, strength of the magnetic field goes on increasing. So that means now what happens? The angular momentum vector started to precess around the direction of the magnetic field. That means as you vary the current through the sweep coil, the Larmor frequency goes on changing. At one particular value of current, what happens? The Larmor frequency is equal to frequency of the applied radio frequency. At that time, the resonance takes place. This is how we are performing the NMR experiment. This is regarding the instrumentation. So next we have to see about FMR, that is ferromagnetic resonance. Let us see what is this ferromagnetic resonance. Ferromagnetic resonance is nothing but the resonance occurred in ferromagnetic material in the presence of microwave radiations. So that is the spin resonance at microwave frequencies of a ferromagnetic substance is called ferromagnetic resonance. Since ferromagnetic materials are highly magnetizing materials, therefore the absorption curve is very, height of this is very large. That means the susceptibility is very large in this case. So that is due to the ferromagnetic substance. So now it can be shown that here, that means what? The susceptibility condition is the same thing as you studied in ESR and NMR. So ferromagnetic resonance takes place when the Larmor frequency is equal to frequency of the applied electromagnetic radiation. So then what happens? The resonance takes place, that is maximum absorption of energy from the applied electromagnetic radiation takes place. That is called ferromagnetic resonance. So now here also we have to consider, since these are the highly magnetizing materials, the local field produced is very large compared to NMR or ESR. Here, that means the condition to observe the resonance, it varies from material to material. Second one is, for a given material, if the material is of in a disc shape, then it has one resonant frequency. If it is in a cylindrical form, it has another resonant frequency. That means even though the material is the same, so now X is the ferromagnetic material. Now you are preparing a ferromagnetic material X, its shape is a disc. Another one, for the same material, you are preparing the sample in the cylindrical form, or you are preparing a spherical shape. Then what happens is, even though the material is the same in all three cases, but resonance takes place at different frequencies. So that means the effective field or the local field changes as the shape of the material changes. Therefore, the condition is the omega naught or omega L Larmor frequency is given by G into E divided by 2mc into H effective. So this is the expression, this type of expression already we have discussed. So now when you are considering to a plane surface, okay, if it is a plane surface, then effective field is B into H naught to the power half. So here when you are considering to this, B is the strength of the applied field, H naught is the effective field. So that H effective is equal to this, B into H naught to the power half. So therefore in the place of this, for plane surface you have to write omega L is equal to G into E by 2 MC into B H naught to the power half. So as you change the shape, the expression for H effective also changes. So now that means what? Let us we consider now the theory of this, just a very brief theory, not in detail. Okay. See, as already similar to NMR, as you know, magnetization M is equal to gamma into G. G is the angular momentum vector, gamma is the magnetostatistical, this here. Now magneto-mechanical ratio, this gamma, then what you have written, dg by dt, these are all similar to your NMR. This is equal to H cross M, then dm by dt is equal to gamma into M cross H. All steps are identical to this. Then the internal magnetic field along x direction, I am writing Hxi, this is equal to minus Nx into Mx. Let us, this is what with the expression we are writing for cubic ferromagnetic material. Okay, so then Hyi is equal to minus Ny into My, Hzi is equal to H naught minus Nz Mz. So that means here Nx, Ny, Nz, these are referred to as demagnetizing factors. That means what? Due to this internal field, if Mx is the actual magnetization, but due to the local field, the magnetization is decreased by an amount is equal to Nx. That means due to the local field effect, actual magnetization becomes Nx into Mx. This much is reduced along x direction. So that means negative sign indicates that actual magnetization is decreased by an amount is equal to Nx into Mx. Similarly, along y direction, the magnetization is decreased by an amount Ny, My. Similarly, along z direction, this is the case. So then, similar to what is the expression for rate of change of magnetization along x direction? This is equal to gamma into, instead of applied field, you have to consider this. The same thing, Ijk, then Hxi, Hyi, Hzi. So Mx, My, Mz. So therefore you have to simplify this. Now M cross H. So x component you have to consider this. So when you are considering this, what happens? It becomes my into hzi minus mz into hyi. Similarly, we are getting the expression for dm y by dt. So that is, in a similar way you have to find out this. That is dmy by dt. This is equal to gamma into, right. So what you are getting, mz into hxi, right, minus mx into hzi. Similarly, dmz by dt is equal to gamma into mx hyi minus my hxi. Then you can substitute the value for hzi. That is, here when you are writing to this my into hz. So hz is nothing but h naught minus nz into nz into mz minus mz into this hy. You have to write now. Hy is nothing but what? Minus ny my. So now you have to simplify this. So when you, after simplification, that is take the common terms outside and collect the terms, gamma into h naught plus ny minus nz into mz into my. So this is the expression you are getting. Similarly, you can substitute the value in case of dmy by dt. So here gamma into mz, in the place of hxi you have to write minus nx mx minus mx, right, minus hzi. Hzi is nothing but h naught minus n into mz. So then you can take the common terms and collect the terms. Then you will get minus gamma into h naught plus nx minus nz into mz into mx. So this is for the expression for dmy by dt. So similarly, you can get the expression for dmz by dt. This is equal to gamma into mx into hyi. Hyi is minus ny my minus my into hxi, that is nx mx. So finally, after simplification, you will get gamma into mx my into nx minus ny. So, but as you know, along the z direction, change in the magnetization is 0 at equilibrium condition, that is dmz by dt is equal to 0. That means, which implies dmz is 0 or mz is equal to a constant value m naught. Okay. So then by solving these equations, we can obtain the expression for resonant frequency omega naught square is equal to gamma square into h naught plus ny minus nz into m naught plus into h naught plus nx minus nz into m naught. So this is the condition for resonant frequency in case of a ferromagnetic substance. So as already told, the shape changes, the resonant frequency also changes. So that means if the specimen is in the form of a sphere, the demagnetization factors nx is equal to ny is equal to nz, then omega is equal to gamma into h naught. This is the condition. See, if it is, just you remember this, if it is a thin plate, then nx is equal to ny is equal to 0, and it can be shown that nz is equal to 4 pi. So then resonant frequency omega naught is equal to gamma into h naught minus 4 pi m naught. So see, third condition when you are considering. See, if it is the thin plate, but magnetic field is applied parallel to the plane of the plate. Here it is perpendicular to the plate. Now you have to apply, it is parallel. If it is the plate, okay, magnetic field should be parallel to the plate. Then it can be shown that nx is equal to nz is equal to 0 and ny is equal to 4 pi. So that means the resonant condition omega naught is equal to gamma into h naught plus 4 pi m naught to the power half. So from all these things, you can observe that as the shape changes, resonant frequency also changes, and also the orientation of even though the thin plate, here magnetic field is perpendicular, here it is parallel to the plate, then what happens? The resonant frequency changes. It is due to the effect of local field changes as the orientation or shape of the specimen changes. It is about FMR. Thank you.